Look up at the night sky, and it's impossible not to wonder, how did all of this begin, and where does it end? For centuries, our answers were strictly local. Early astronomers, looking through rudimentary lenses, placed Earth right at the center of everything. Eventually, Copernicus and Galileo bumped us outward, proving we orbit the sun. But even then, the consensus was that the universe as a whole was static, fixed, unchanging. Then Isaac Newton realized a major mathematical problem. He discovered that gravity constantly pulls all mass together. If the universe was truly standing still, the gravitational pull of every star and galaxy would eventually drag everything inward, crashing into one massive center point. A stable, unmoving universe couldn't exist. It had to be either expanding outward or collapsing inward. The solution to this paradox arrived with Albert Einstein. He realized the three dimensions of physical space and the fourth dimension of time aren't separate. They are woven together into a single, continuous fabric, often compared to a stretched sheet or chauder. This space-time fabric governs the movement of planets, stars, and galaxies. But when physicists began looking at the microscopic scale, down into the behavior of atoms, electrons, and quarks, they found something alarming. The smooth, predictable rules of Einstein's stretched sheet completely fall apart. Science suddenly found itself divided. We had one beautiful mathematical rulebook for the massive objects in the cosmos and a completely contradictory rulebook for the microscopic building blocks of reality. Let's look at the large-scale rulebook first, general relativity. If you place a heavy object like the sun on that space-time fabric, it creates a deep depression. A smaller object, like Earth, doesn't just float through empty space, it rolls along that exact curve. That curve is what we experience as gravity. In 1929, an American astronomer named Edwin Hubble looked through a massive telescope and observed something that solved Newton's old dilemma. The universe wasn't static. This diagram illustrates what Hubble saw. Just like a train horn drops in pitch as it drives away from you, light does something similar. When a galaxy is moving away from us, its light wavelength stretches out and shifts toward the red end of the spectrum. Hubble noticed that almost every distant galaxy was showing this redshift. The entire cosmos is actively expanding, like dots on an inflating balloon. The macro-universe operates as a predictable, stretching fabric dictated entirely by gravity. Now, let's zoom in. When physicist Werner Heisenberg established the principles of quantum mechanics, he proved that the microscopic world doesn't care about predictable curves. At the atomic level, you cannot measure a particle's exact position and its exact speed at the same time. If you use light to observe an electron, the very act of the light hitting it changes its speed. Down here, reality runs on pure probability. These two separate realities, the predictable macro and the uncertain micro, usually stay in their own lanes. But there is one place in the cosmos where massive matter is crushed into an infinitely small point of zero size, a black hole. Here, infinite gravity meets a microscopic footprint, and both rulebooks crash. Theoretical physicist Stephen Hawking realized that to understand the universe, he had to figure out what happens at the very edge of this boundary. Watch the edge of this black hole. Empty space is never truly empty. Microscopic pairs of particles constantly pop into existence. Hawking proved that right at the boundary, one particle is swallowed by the infinite gravity, while its partner escapes into space. From the outside, it looks like the black hole is emitting radiation. By proving that the microscopic quantum world interacts directly with massive gravitational fields, Hawking showed that black holes leak energy and will eventually evaporate entirely. If space-time is a flexible fabric, it raises a strange question. Why can we move freely in three spatial dimensions, but time only ever drags us forward? Physics points to the thermodynamic arrow of time. The universe naturally moves from a state of order toward a state of disorder, or entropy. A whole cup is order. The shattered pieces are disorder. We never see those pieces spontaneously reassemble because the mathematics of entropy favors the spread of energy. This lines up with the cosmological arrow, the expanding universe, and our psychological arrow. Our brains burn energy to record memories, generating entropy in the process. This alignment ensures we remember a past, but face an unknown future. This rigid direction dictates the possibility of time travel. Traveling near the speed of light could allow you to return to Earth decades in the future, but backward travel remains physically elusive. Hawking's chronology protection conjecture suggests that the laws of physics may simply make past travel structurally impossible, preventing the logical contradictions of the grandfather paradox from ever occurring. The synchronized movement of these three arrows creates the linear reality we experience. Today, science is still searching for a single mathematical framework, a theory of everything, that can reconcile the predictable curves of gravity with the chaotic probabilities of quantum mechanics. Such a discovery would finally bridge the gap between the curvature of space and the behavior of particles, offering a single mathematical description of the universe's beginning and its end. Yet, in the middle of this vast, complex system, our entire world is just a speck of dust suspended in a single spiral galaxy. Because our timeline is finite, and our microscopic world is built on inherent uncertainty, our most powerful tool is not control, but curiosity. In an infinite universe we cannot reverse, the value of each moment is defined by our drive to understand it.